Indeed, yeah. I want to talk to you about dynamical instabilities in the planet formation, circumstellar disks. And actually, I would like to start with an advertisement. We're hiring postdocs. We're hiring up two. One is this position that has been advertised, and I'm going to advertise another one for my group. So we're hiring two postdocs next year. This is Las Cruces, if you haven't been there, the beautiful Oregon Mountains, and this is our group. But I guess that a much better incentive for people here in this room to consider a postdoc there in New Mexico is, I guess, the price of rent. I heard that the average rent in New York is like 4,000 right now. There's average rent there in Las Cruces. So, there you go. Well, the outline of this talk, I'm going to talk about planet formation. Second part is going to be about disk instabilities. And then the last one, how to tie it all with disk observations. So let's start from the beginning then and talk about planet formation, how the planets form. So first, for the people who do not work in the field, I'd like to give a brief introduction to the numbers that we deal with so that you can have a feeling for what these protoplanetary disks look like. So they are objects that have a density of about 10 to the 13 to 10 to the 15 particles per cubic centimeter. For comparison, the density of air is 10 to the 21 particles per cubic centimeter. The temperature range from about 10 Kelvin in the inner part, in the outskirts of the disk, to about 1,000 Kelvin in the inner parts, closer to the star. Range scales from 0.1 to 100 AU. And the masses range from 10 to the minus 3 to 10 to the minus 1 times the mass of the sun. Right? And this is the basic view of how planets form. Planets form in disks of gas and dust. Right? You have interstellar dust. Right? Between stars, you get them in this disk, and then somehow they form planets, right? Of course, our job is to explain exactly how this miracle happens. Well, of course, we know a little bit more than that. Essentially, if you start from the micron-sized grains that you find in the ISM, you can grow them by coagulation, right? Heat and stick mechanisms up to about millimeters, centimeter in size. And then if these objects grow beyond the kilometer size, gravity comes to assist, right? And if they get very, very big, then they accrete gas from the nebula and become a gas giant planets like Jupiter. But in the middle, then, there is something here happening, maybe something, right, that we are not exactly sure exactly how that would be to breach the sizes then from centimeter sizes to kilometers. Because at this point, these objects don't have enough mass to attract each other gravitationally, right? But they are already too big to keep growing by heat and stick mechanism. So we need something else. What is this something else? For that, we need to find collective mechanisms to assemble the pebbles and then grow them to the sizes of planets. Now, there is another problem here too, is that the gas and the pebbles are moving differently in the disk. Right? The gas has support from the pressure gradient and the centrifugal force. Right? So there is the gravity from the star, but then you have the centrifugal force from the orbit and a little bit of the pressure gradient too, because the gas close to the sun, to the star, as I said, is hot and dense, and the gas here is thin and cold, so you have a large scale pressure gradient. The pebbles, though, they're not feeling this pressure gradient, right? It only affects the gas. So they're orbiting at the speed that a planet would, right? Just in balance between the gravity from the star and the centrifugal force. This mismatch between the speeds of the gas and the pebble makes so that the pebbles feel a headwind. They lose angular momentum and drift towards the star, right? So this is a calculation here where you're solving for the coagulation and considering also the drift. So you have here the particle size, right? They are coagulating to bigger sizes, and then the distance to the star. This line here is the line of maximum drift. So the pebbles grow to the size and then drift towards the star. So if this is the full picture, planets shouldn't form. You grow them, they drift, you lose them out to the star. But last I checked, we're standing on a planet, so we have good evidence that they exist. So what is wrong here? One thing that is missing is the realization that this drift is itself hydrodynamically unstable, right? whenever you find an equilibrium or a steady state solution, you have to ask if your equilibrium is stable or unstable. It turns out that this drift of the pebbles is unstable. So it is not orderly. It's going to turn into regions that are of higher density and regions of lower density. This is the so-called streaming instability that many in this room here work on and many have heard of. What's going on here is that you have the drifting, you have a drift, sorry, let me replay this. It's buffering. Wow. You have a drifting dust clump, right, moving inwards due to the drag force. Because it is moving inward, the Coriolis force will deflect the dust clump. So then what you have is that the gas now, instead of giving you a headwind, it's giving a tailwind. It is giving angular momentum to the clump. It will make then the clump move outwards and then reinforce the dust clump. And that's how then you have this traffic jam that will make the density of the clump go up. And still buffering. Do I need to restart here? Yeah, you see here, it's spinning. Oh, there we go. Oh, actually went one further. Right, and this was modeled by Anders Johansen and Mordecai. This is a video that was actually made here in New York in the museum, showing the highest concentration that you get of pebbles in a calculation, including also the self-gravity of the pebbles to follow their collapse into planetesimal. Turned out that the most massive object, which is this one, is 3 times more massive than Ceres, the most massive asteroid. So this is indeed a way to bypass the fact that the pebbles don't continue growing. You concentrate them mechanically, and then they can achieve the critical densities to collapse in the form of planetesimals, right? Well, this is good news then, because we think that there is some sort of turbulence happening in disks. This is a calculation done by Mario Floch now in Heidelberg in Germany, showing what I call the magneto-rotational instability in protoplanetary disks. It's an instability that happens when the disk is magnetized, right? You have here the disk being completely magnetized. This is ideal MHD. The shear in the disk will make the magnetic energy grow, and then you set the whole disk in turbulence. It was showing the RMS speeds, and now in blue here showing the degree of magnetization. So the white parts are less magnetized, the dark parts more magnetized. Right? So this is a very good way to lead to turbulence in disks, and that is good news, because if you need the transients to capture the dust in for long enough times to collapse them to planetesimals, this is exactly what turbulence does. Turbulence is a way to generate lots of transient high pressure regions all over the disk, right? And then in each one of these high pressure regions, you would be able to concentrate the dust, right? So this is a calculation that I did, throwing pebbles in a model that had the magnetorotational instability in the gas phase. What you're seeing here is the dust. So what you see is that soon the pebbles get caught in the overdensities of the gas, and the brighter areas are supersaturated with pebbles, and then eventually it would lead to collapse, right? And then form a planetesimal. So all seems to be fine, except that there is a big problem in this picture. Because if you need a mechanism to generate turbulence in disks, that depends on the magnetization. Magnetization is not going to be achieved in vast swaths of the disk, because these disks are cold, right? So if you have a mechanism that depends on the magnetization, you also need ionization. In the inner part, there is enough ionization because the disk is here, I mean, the gas here is hot enough to be ionized by collisions, right? The molecules hitting each other lead to sufficient ionization. And in the outer parts, even though the disk is cold, the column density is thin enough that X-rays from the star and cosmic rays from the galaxy can go all the way through and give you ionization for the whole column of the disk. But in this region here, shaded brown, the disk is going to be too cold and too dense to be ionized either way. It's not going to couple to the magnetic field. The magnetorotational stability is not going to happen there. So I was interested in that and to see what would happen here if we model this hydrodynamically. Also because this is precisely the region where we expect the planets to form. It goes from about 0.1 AU to about 30 AU. That's where the planets in the solar system are. So if we want to form a planet in this region and we need some turbulence to concentrate the dust, we need to find something else. So I wanted to model hydrodynamically what would be happening in this dead zone. So this is one of the earliest models that I ran about this problem, showing here that there's something funky happening in the borders, right, of this dead zone. So you see, this is breaking in some sort of instability, and so now this inner one is also showing signs that it's something interesting is happening there. So this was done in a purely hydro model. You can model that also in an MHD calculation. That's a work I did here also in New York City with Mordecai. We magnetized the inner part of the disk, and then we had a dead zone, a resistive outer disk. And you see that in the border between the two regions, there is something happening there too. The same thing that we saw in the previous calculation. If you model it long enough, you see that there is some interesting dynamics happening there. You form this giant entity in here. This is a vortex. This is happening because you have an extra shear in this boundary between the active region, the region that is magnetized, and the region that is not magnetized. And whenever you have extra shear in the boundary layer between two fluids, you excite the Kelvin-Helmholtz instability. You have a mode here, so you have the shear. So this part of the wave is traveling faster than this part of the wave. You change the shape of the wave front, and then it will tumble into these billows. And that's what you see here. Example of Kelvin-Helmholtz instability in the atmosphere, between the atmosphere and the clouds. And vortices, they are ubiquitous fluid mechanics phenomenon. You find them pretty much everywhere. You find them in the atmosphere of the giant planets, find them as hurricanes on Earth, as whirlpools in the ocean. And this is one of the most beautiful phenomena in fluid mechanics, the von Karman vortex street. You see here the vortex street on the flow in the atmosphere to where the obstacle here is the column of air over an island. And so you find these things everywhere. And vortices have a very good property for planet formation, is that they also behave like high pressure regions that will help trap the dust. Essentially, the same thing that was happening that will lead to a drift of the pebbles in a protoplanetary disk is happening in a vortex too. In a vortex, you have what are called geostrophic balance, which is a fancy word just to say that the Coriolis force is being balanced by the pressure gradient. And then as a pebble enters it, it doesn't feel the pressure force. It's not only the Coriolis force and the centrifugal, but also the gas drag. And the gas drag will make them spiral towards the center. This is what you're seeing here. This is a model of the pebbles, but in a calculation where we had a vortex in the gas phase. So the pebbles are drifting towards the center, but there is no star there to burn the pebble in flames, right? So they just accumulate more and more and more and more, right? So it's a very good way to form planets. The grains will not feel the pressure gradient, they sink towards the center, accumulate, and then you can form very high mass objects in there. So this is a paper that I am working on right now, following the gravitational collapse of the pebbles into planetesimals. So here you see 3 snapshots in time, right? This is after 2 orbits. So big T here is 1 orbit. After you add the pebbles in the calculation. You see here the vorticity in the gas, tracking right the degree that the gas has vorticity, and the pebble column density in here. So you see this accumulation where the vortexes, and these dots are protoplanets that formed in this calculation. So already after 2 orbits, they already formed some of them. After 5 orbits, they form and they leave the vortex. You have many of them. After 12 orbits, they're pretty much everywhere. Right? And when you compute the mass function, how many of these protoplanets you formed at each, so these are 3 calculations at 3 different resolutions from 128 cube to 512 cube. The green ones, 128, 256, 512. You see that you have a convergence here for the higher masses. And as you increase the resolution, you form more and more of the low mass ones. Right? This is the cumulative mass distribution. You see that it follows a power law here in the initial mass function of index 1.6. But the masses, look at the masses that we're forming here. So first, when you do these calculations, we use unitless, right? So I was measuring the masses in gravitational masses. All right, so 10 gravitational masses, 20 gravitational masses, and making this plot, okay, like let me convert that to physical units, and bam, like look at in Earth masses, how big these things get. So this goes here from, so 1 Earth mass, right? This is Mars mass, this is the Moon mass, right? And so this, you can form very massive objects by trapping them in vortices. This is how the calculation is going in time. So as the time goes here, I calculated this for about 300 orbits. You see here, as it reaches the critical density, the Roche density, right? You have a burst, and then the number saturates because you don't reach the critical density anymore. So the number of protoplanes is shown here. They just cascade down, and then you have convergence of the distribution of planetesimals. I'm showing here like the Moon mass and the Mars mass. So it seems that it has converged in time. So the take-home message of this part of the talk is that there are 2 routes to form planets. One is extreme instability, the other one vortex trapping. One seems to happen in the active zone, the other one in the dead zone. And we still don't know yet how turbulence helps to concentrate, how turbulence will interact with the streaming instability. If it's going to help concentrating the pebbles at the larger scales of the flow, as we see here, right? Or if it's going to hinder, that means that the turbulence will lead to too much diffusion at the small scales of the flow. So that's one open question. And also, there are other types of these instabilities, and we want to know also how they interact with these mechanisms to form planets. So I'm going to pass now to this second part of the talk, discussion of these instabilities. We know that, as I said, yes. You have a question?
Yeah, it's a question. Thank you. Just wondering. I don't know this at all. Like, is there any differences in the output of the different formation scenarios?
Mm-hmm.
Do it forms planets differently in terms of the output?
Mm-hmm. Mm-hmm. Yeah. So as I said, I was surprised about how big the masses here are. Streaming instability is forming objects in the calculations that range between 10 to the minus 6, so about the mass, 10 to the minus 6 times the mass of the Earth. So it's about 0.1 series mass, right, to a few times series mass. The formation mechanism, the streaming instability formation mechanism seems to saturate at about 10 times the mass of series. No calculation has seen masses higher than that. So series about 10 to the minus 10 to the minus 6. So it should be around 10 to the minus 5. So 2 orders of magnitude less than this. This mechanism here is forming much more massive objects, right? Yeah. But thanks for the question. That was something that I was thinking here. If this is even converged or not. In fact, I ran lower resolution models of this some 10 years ago, and also saw Moon mass objects, Mars mass objects but in global disk models where the resolution was much less. So one of the things that I was wanting to find here, I mean, to check with these 3D models, is if we would find lower masses, if we would find convergence at the lower mass, and we still don't find, and the masses that we form are still Moon mass and Mars mass, right? So yeah, like 10 years ago, I was saying, like low res. Yeah, I mean, we put high res and we still find the same thing. It seems, yes. But this calculation, yeah, I ran also one of 1,028 cube. It's been running for some months. And so I need more computer power. Right, thank you. Right, so back to the dead zones. What is going on? So you saw that the disks must have a magnetized active zone and it must have a non-magnetized dead zone. But there is more in the dead zone than just calling it dead zone. In fact, in the past few years, we found a lot more instabilities going on there in the disk. As I said, in the inner part and in the outer part, so this is a scheme, a map, an instability map of the disks. We have here the MRI, right? As I said, in the very inner part where you can magnetize the disk a lot due to just collisions, and in the outer part where the column density is very thin, right? So the streaming instability we're putting here in the middle of the disk, in the mid plane, right? High here, 0.1 in AUs or so, because the dust sediments, right, to the mid plane of the disk, and that's where this should happen. In the very outer part, I mean, in the very upper parts, you have emitted winds, right? Photo-evaporative winds, like that the gas gets so thin, right, and it gets evaporated by the energy that it gets from the star, and also on magnetocentrifugal winds. And in the omic zone, it turned out that the community has identified the three promising instabilities that may be happening there: the vertical shear instability, the convective overstability, and the one that I'm renaming here, resonant buoyant instability. Here, though in the literature, you're going to see that called zombie vortex instability. Yeah. But I think that yeah, resonant buoyant instability makes more sense, and I'm going to explain why. So for the vertical shear instability, the mechanism is shown here. So you have here the angular velocity contours in the disk. This is the radius in the z direction, and this is an angular momentum contour, right? So as you start the calculation, you see this happening here. You see these fingers going through lines of constant angular momentum, right? As you have this gas parcel here at A, if you move that to B, it's going to find itself in a region of lower angular momentum, and it will continue going on and on, right? So this is the vertical shear instability. It is triggered when you have a difference, right, in speeds, so a shear in the vertical direction. Natasha Munger, that was here, right, at the CCA, was working on that. This is also a vertical shear instability calculation done by a student on Hubert's group, Thomas File. Beautiful plot. As you can see here, showing several different quantities in the same plot. You have the vorticity, it's shown here in the mid plane, and here the Reynolds stress. For the experts in the field, that's the alpha value. Here, the Reynolds stress, right, is the, the alpha value is the normalization of the Reynolds stress by pressure. When you have this, when you have a value of about 10 to the minus 2, it ends up matching what you will find from the mass accretion rates measured in the observations. So you have a Reynolds stress of about 10 to the minus 4-ish. Right? So not that much, it doesn't lead to that much accretion, but as you see, it leads to all of this structure in this. So that's very interesting for planet formation, because as you saw, vortices are very good for forming planets. The second instability would be the convective overstability, which is another work I did here in New York. And what you see here is you can start this calculation with just pure white noise, right? You give some amplitude, and then you see that the vortices form. Then what is going on is pretty much the same thing that is happening in stars, convection, right? You have hotter gas here and you have colder gas here, Just that in a star, there would be the surface and this would be the center. In this case here, this is the orbits that are closer to the star and the orbits that are further from the star. This is a figure actually from Field's review back in 2010. Right, you have this entropy gradient here, right, makes so that if a gas particle rises buoyantly, right, it reaches this outer orbit here with more entropy than the ambient gas. And then in this lag, it's going to be thermalized, but now because it lost entropy, it's denser, so it's going to sink. And then in this lag, it's going to thermalize back and then you close the cycle. And then this way, you generate baroclinicity and keep the vortex alive. Right, so we call this the convective overstability when it comes to disks. You need two things for that, which I already hinted here, which is you need a radial entropy gradient and you need a finite cooling time. Okay, thought I had written here, but it's not showing. Right. Well, I'll go back to it. And the third mechanism then would be the resonant buoyant instability or the zombie vortex instability. What is going on is that if you have a perturbation anywhere in the disk, the epicyclic frequency of that oscillation is going to find a resonance with the buoyancy frequency somewhere in the disk. So that is going to excite that resonance that is also going to be amplified, right? It's a resonance. And now this new resonance, the epicyclic frequency of this perturbation is also going to find a resonance with another buoyancy frequency elsewhere, and then the whole thing cascades. That's why I'm calling it a resonant buoyant instability. They call it zombie because it happens in the dead zone and it's sketchy. So, yeah. Now, these three mechanisms, what I find amazing about it is that they all happen in different regimes of cooling time. So they can be translated into different opacity regimes. Right? That's why you can map them to different locations in the disk. The vertical shear instability happens because you have a vertical shear and something that is moving outwards, continues moving outwards. So buoyancy stabilizes that, right? An entropy, a stable entropy gradient will make that stabilized. So in fact, the most unstable mode is isothermal. The vertical shear instability will happen mostly when you have very fast cooling times, right? The resonant buoyant instability is the opposite regime. You need a resonance between the epicyclic frequency and the buoyancy frequency. So it's only going to happen for more adiabatic regions of the disk. You need the buoyancy for that to happen. And the convective overstability is in between, in finite regimes of cooling time. So this happens on the disk as isothermal, this happens on the disk as adiabatic, and this in intermediate ranges of cooling time. You can translate that to different regimes of opacity and map it into different regions of the disk, which is why I showed them in this progression, right? This is in the inner part, more massive, like more, the density is higher, more optically thick. The vertical shear in the outer part where it's more optically thin. Right. And even more amazing for planet formation is that they all saturate into vortices. So this will be the take-home message of this second part of the talk. Right? The vertical shear instability saturates into vortices. The resonant buoyant stability also saturates into vortices, and the convective overstability also. So we have these three different mechanisms to generate structures in the dead zone of disks, and they all lead to vortices. Finally, what does it have in, what does this all have bearing with on the observations, right? So this is H al tau, as you all know and we all know and love. H al tau is an example of a transition disk, right? So a transition disk is it's a name that confused me a lot when I started working in this field. I was like, what, transition into what, right? Well, turned out that a transition disk simply means that it's a disk with a hole. So this is the spectrum that you get from a typical disk, right? You have here the black body of the star, right? And then you have here the infrared axis from the disk, right? And here then the Rayleigh-Jeans scale in millimeter and radio wavelengths. Turn out that the spectrum of a transition disk is missing. It's missing the hot dust. Right? It's missing the infrared. You have here the black body of the star. You have the millimeter axis, but it's missing here all of this infrared axis, this near infrared axis that is seen in the classical Titori, CTTS classical Titori star. Right. The interpretation for that is disks with a hole, right? Disks that are missing the hot dust, right? So this is the model for a transition disk. Right? There's a star, there's a disk that goes beyond, and then you have a hole here in the center. So a model density map here, you pass that through a radiative transfer code, and that's what you get, right? You have here these inner parts, right? This ANSI, and then the hole in the middle. Well, turn out that there are, then I have to explain, right, where this hole comes from. The nomenclature transition is because it was thought that the main way to generate this gap here, this hole, would be by photo evaporation. So these would be disks that are transitioning from a gas-rich state to a gas-poor state, and then you get rid of the gas from the inside out, evaporating it from the inner parts. It turns out there are other ways to generate this that are not immediately connected to disk evolution. So transition disks may not just be transitioning, right, from gas-rich to gas-poor. It may simply be that these are disks with planets, right? So how would you carve that hole if you have a planet in there? So you have the accretion flow in here. You put a planet there. The planet carves a gap, separates the outer disk from the inner disk, blocks the gas from flowing in. The inner disk empties onto the star, and then you have just the outer disk and a companion. Then you generated a hole there in the disk, right? So that means that these cavities could be telltale signatures of forming planets, right? So what do we see them in a calculation with a planet? You see spirals, right? You see vortices here in the edges of the gap, right? And you see the gap. So this is one of the few instances where a planet has actually been seen inside the gap of a star. That's the disk around the star PDS 70, the planet here, PDS 70b. Found a new planet also, the PDS 70c, right? So planet disk interaction leads to gaps, spirals, and vortices. And when you look at the structures that ALMA is seeing around disks, this is exactly what you see. You see gaps, spirals, and vortices. Of course, not in the same disk, but you see precisely these three types of structures that have been predicted by numerical simulations. So H.L. Tau here, beautiful example of these rings and spirals. I mean, spirals here and SAO 20656. And Ophiuchus IRS 48, beautiful example here of maybe a vortex. You see that there is a bigger concentration of dust all in one side of the star only. And I'm going to go back to it. So this is being possible due to ALMA, right? The Atacama Large Millimeter Array. And people are calling this the ALMA revolution. Guys, it's just the ALMA resolution. Right? That's where the revolution comes from. This is what could be done way back when, right? I mean, if you put the solar system at 140 parsecs away, this is what could be done before ALMA, and this is what ALMA can do. Right? So that's how much better the resolution got. That was done. That was H.L. Tau observed with Karma, and H.L. Tau observed with ALMA. So fantastic. Well, the structures, right, that are seen in disks also became much sharper. That was what could be done back in 2012, right, with ALMA cycle 0, and what is what ALMA is doing now. Right? So way better resolution. Right. And indeed, you can see here some objects, right, that have what look like vortices in here. Right? This one, that's AS209. and Ophiuchus IRS-48. As I said, it's a huge vortex that was observed with ALMA. So let me explain here this observation quickly. So you have here the observation with ALMA. ALMA is tracing the millimeter dust grains. So they all seem to be on one side of the star, right? This is the observation of the gas. So you have the gas here that is being blue shifted, so towards you, and then the gas that is being red shifted. So it's obviously something that is executing capillary rotation. And then the micron size dust grains observation in infrared that is in brown here. You see dust all over the place. So there's something that is filtering the bigger grains only, but not the small grains. And yeah, we could explain that with drag diffusion, with drag and diffusion equilibrium inside a vortex. So here I'm gonna break one of my first rules of giving talks, which is to never show equations. But this is the dust continuity equation. You have the advection term, the compression term, the diffusion, right? You have here the drag force, right, and the diffusion. What I wanted to do here is to find the steady state between the drag force pushing the pebbles inwards and the diffusion kicking them outwards, right? Because if you are seeing that in an observation, some steady state maybe, has to be happening there, otherwise we wouldn't see it, right? So in those models that I was showing before, you trap the dust all inside the vortex, but you don't see them being diffused outwards. The diffusion is of course due to the turbulence. Right? So essentially is getting to solve this equation here, cancel the time evolution and find a steady state. Well, I learned back in grad school to go analytically as far as one can and only run simulations when we cannot go any further. Turned out that in this case, we could go analytically all the way. So this is the steady state solution. It depends on a few quantities. And the quantities that I'm showing here, the vortex on my minor axis, the scale high, vortex aspect ratio, delta is the diffusion parameter, Stokes number, which is the size of the grain. It's a model dependent function. Basically on these three quantities here, the scale height of the disk, the aspect ratio of the vortex, it's quantity S here, which is the Stokes number over the diffusion parameter. So it was quite fun to play with this function here and try to fit it to the observations. Turned out that, yeah, that's a very good fit. So this is another disk that has what looks like vortices in them, MWC 758. You see here like these two lobes, right, that dust is being trapped in them. What you're seeing here is an overlay, right, with a sphere. So that's observation in infrared. That's this ANSI that you see here. ALMA, it's the blue contours, and then VLA, the red contours, right? So ALMA is tracing the millimeter grains, sphere in infrared, the micron grains, so on the surface of the disk. And VLA then is tracing even bigger grains than that, right? Centimeter size grains. You see that there is a spatial collocation, right, between the VLA contours and the ALMA contours. This was what could be done in 2015. As you see, ALMA is adding more antennas. This is what could be done with ALMA and VLA in 2019. So much sharper features there you see. So you can combine the ALMA observation with the VLA observation. You fit them here and you see that the VLA contours are indeed smaller than the ALMA contours. So this fits with the results that we get from the models that as you trap the dust, the bigger grains, right, the higher Stokes number will concentrate more than the smaller grains. So this is a simulation here where you have the vortex in the gas phase, the small grains, Stokes number 10 to the minus 2, right? So millimeter, centimeter size. So that's what ALMA would be seeing. And VLA would be seeing more this type, so much more concentrated. So this fits quite well with the observation. They are calling this analytical vortices, seen then in MWC 758. So take home message here, vortex trapped dust in drag diffusion equilibrium explains the observation. So concluding, what is in the future? So nearly all nearby disks observed at sufficient resolution show substructures, right? The types of substructures that are seen are crescent-shaped, have spiral arms, rings, and gaps. And what is it that we can expect in the future, right, with more instruments? You know, lots of people are super excited about JWST. I am too, but I want to have more resolution. So in fact, I'm excited about next generation VLA, right? I want to get here to this part so that we can see even more stuff, right? So this is what ALMA can do now, and this is what NGVLA is promising to do, right? So if you put Jupiter, Saturn, Neptune in, you know, in a SPERF at 140 parsecs in the nearest star-forming regions, VLA would be able to see this. We would be able to see Jupiter, right, at 5 AU, right? This is what, this is Jupiter here, right? NGVLA would be able to resolve that. So I'm definitely looking forward to that. New Mexico has a bright future. Conclusions, then there are two routes for planet formation, the streaming instability and the vortices, and they seem to be complementary. Open question, if turbulence helps concentrating the pebbles at the larger scales or hinders because of the diffusion at the small scales. There are three dynamical instabilities in the recessive that zone. They operate in very different regimes of opacity, therefore in different regions of that zone, but they all saturate into vortices. So super curious about how they form planets. And dust trapped in drag diffusion equilibrium in these vortices seem to explain some of the observations. These are some of the open issues, right? Are the dynamical instabilities responsible for the observed crescents in the observations? What is the overlap between these instabilities? They have never been modeled in the same simulation. We still need the global models of some of these instabilities, chiefly the convective overstability. The relevance of the resonant buoyant instabilities is still unclear. And what are the planet formation properties and their synergy with the streaming instability? So this is my check table of stuff that I want to do in the next few years. So some of them have been done, some of them haven't. Thank you very much, and I will be happy to answer questions now.
Okay, so yeah, we're now ready for questions. People on Zoom, feel free to type in your question in the Zoom chat.
Really nice talk. I learned a lot, actually. On does turbulence help or hinder? I mean, what would it take to answer that question? Like, could you do a numerical experiment where you change the level of turbulence in the disk? Is it a resolution issue? Like, how would you go about designing a numerical experiment to try to answer that?
Yeah, well, excellent question. Thank you. Indeed, yeah. One of the guys in the collaboration, so this is the TCAN collaboration, I mean, the TCAN that we got in 2020. Orkan, actually, that's he's in Ames. That's what he's doing right now, actually. So the model that he's using to answer that, yeah, it is a streaming instability calculation and indeed throwing more resolution at it, and then also using particles of different sizes. And that's quite interesting to see the results that we are seeing from them. Indeed, what we see so far is that this continues happening, right? To have the trapping of the bigger grains in the bigger eddies of the simulation, but there are eddies all over, right? Like that's what turbulence does. There are eddies at scales that the bigger grains are expelled from them, not captured. So these grains that get expelled from the small eddies end up concentrating between eddies, like not in them. So there may be even another way to form planetesimals that has been called in the literature turbulent concentration. So yeah, the main question then would be to see what is the relative importance of this method to form planets, the streaming instability, or the turbulent concentration, the capture of bigger grains in between small eddies.
Can I ask about the connection between the first and the last bit of the talk?
Of
So
course.
for the dust, the vortex concentration diffusion equilibrium, when you sort of reach that equilibrium that matches the observations, how close would you be to perhaps reaching the Roche density and forming objects in that kind of situation?
Yeah. Well, excellent question too. Thank you. Yeah, maybe I'm wondering about that as well. And yeah, we do see the. I thought I had a. So yeah. So yeah, okay. Yeah, you trap the dust right in this vortices, and then as you added the feedback of the grains, you see that it breaks down, right? So you have not like one single concentration; it breaks down into many different ones. So we end up seeing that at some points, right, the disruption gets very well. I mean, like you end up concentrating so much dust, you disrupt the vortices. So this is what you see here if you have a dust to gas ratio of 10 to the minus 2, right? So you don't see anything else in the midplane anymore. And then at 10 to the minus 4, you still see, right, some trapping happening there. What I showed was that this is something that happens only though in a 2D case, but in a 3D case, so this is a 3D calculation with the vortices being trapping the dust, right? You see that so this is the midplane, right? This is with the back reaction. This is without the back reaction. So if you only had this view here in 2D, you would conclude that the dust trapping eliminated the vortex completely. But as you can see in the 3D case, the vortex continues like up and above and below the midplane, and this is the dust trapping. You can see here there's still some dust right that is being trapped in the vortices. We followed this trapping to see how dense, right, it would get in here. So this is showing the maximum dust to gas ratio, right, that we have in this different calculation. So this is for Stokes number equal 1 and Stokes number 0.05, right? And for Stokes number 0.05, if you start from 10 to the minus 4, right, dust to gas ratio, you don't, well, I mean, you reach here. So all of them here seems to reach dust to gas ratio equal 1. Yeah, it takes, I mean, it doesn't go much beyond that, but it gets to dust to gas ratio 1. All models here, right, all the Stokes number that we tried from all dust to gas ratios that we start with, there are some regions inside the vortex that lead to dust to gas ratio 1. Now in this model, we didn't have the resolution to capture the streaming instability, right? So, but that's entirely possible that these regions here that reach the dust to gas ratio 1 would trigger the streaming instability. That's actually something that I want to do with these models here to increase the resolution in the 3D models that I showed, so that we can resolve also the streaming instability in them. But I needed to publish this paper first, and then I'm going to do that.
Great talk, Vlad.
Thanks.
I'm wondering how much of this can we steal and apply to the outer dusty regions of AGN disks, because this sort of stuff has to apply
Right.
in other parts of the disk. So what can we do? What can we do?
Yeah. I was a postdoc in New York here, 10 years ago, and I heard the same question from Barry, and then there's a whole new field about this. Great, yeah. I'm curious about that too. Yeah. So how much of this, right, can we apply to AGN? I would say that the main difference between AGN and protoplanetary disks, if you apart from mass, size, and this, of course, like. If you scale up, right? If you scale up, if you take a protoplanetary disk and scale it up to the sizes of an AGN, a lot of it can still apply. The main thing though is the ionization, right? The ionization would probably not be the same because what we're having here is what is ionizing the disk is the X-rays from the star, right? It's you only have collisional ionization in the inner part, right? Essentially, protoplanetary disks are passive and aging disks are active, right? So the degree of ionization probably will change this. And I would imagine that most of the AGN is MRI active, right? Most of the protoplanetary disk is not, right? It is too cold and too dense, it's dusty. But there are regions, of course, of an AGN that are also cold and dusty. So if this is happening there, I'll be happy.